Okay, so last time we worked through the definition of eigenvalues and eigenvectors and did a lot of examples of those. The check-in is to do one more of those, and then today is kind of an extra section that covers just a very small topic about the geometry of eigenvalues and eigenvectors. Okay, so let's have a whack. All right, so let's see here. I'm looking at the transformation of the plane that takes xy and goes to minus x and 2y. Okay, so pretty straightforward transformation. And I'm asked to first represent it with respect to the standard basis, so some pretty easy bases. So let's see, I've got to figure out where do the standard basis vectors go under t. And I mean, it's, so it's minus 1, 0, and 0, 2. And then I have to figure out how to represent that with respect to the standard basis and represent that with respect to the standard basis, and I'll put it into a matrix and then I'll be done. So it turns out that this is all pretty easy. So representation with respect to the standard basis of t equals, we can do this by I. So how do you represent that with respect to the standard basis? Why, with respect to the standard basis, any vector is represented by itself. So that's how. And how do you represent that with respect to the standard? Well, I hardly got the words out of my mouth when a person knows right away what the answer is. So the standard basis makes the whole job, boy, so much easier. All right, and then question 2 says, figure out what's the story with the eigenvectors and eigenvalues of this matrix here. So 2. So of course, what we're looking at here is we're looking at solving minus 1 minus x, 0, 0, 2 minus x by b1, b2 equals 0, 0. Okay, and what we learned is just to follow through the steps that we learned. I'm not claiming that this is hard to do or anything. I'm just following through the steps that we learned. Is you take the determinant of t minus xi, that's this matrix right here, and you figure out when is it equal to 0. And the determinant of t minus xi, because t minus xi is a diagonal matrix, also upper triangular, is pretty obvious, and it's also obvious how to factor it, that it factors as minus 1 minus x and 2 minus x. And so x equals 2 and x equals minus 1 are the two solutions to that equation, so to that characteristic polynomial, the roots of that characteristic polynomial. So I'm going to write down that the first eigenvalue is minus 1, and I'll find the associated eigenvectors, and then the second eigenvalue is 2, and down here I'll find the associated eigenvectors. So really, other than the fact that this is kind of algebraically easy, it's all the steps that we ordinarily go through. But it is algebraically easy, I have to say. When you put in minus 1 here, right here, when you put in minus 1, you end up with a system that says 0b1 equals 0, and then 3b2 equals 0. And it's easy to see, of course, how to solve that. Oops, the sun has come out. It's easy to see, of course, how to solve that. And you get here that b2 is 0 and b1 is not 0. b1 is free. b2 is 0 and b1 is free, and so we get that the associated solutions look like this. Okay. So it's all the multiples of the standard basis vector E1. Complex multiples, but anyway, multiples. And likewise down here, this is similar. You get, let's see here, when you plug in the root of the characteristic polynomial, when you plug in 2, minus 1 minus 2, so you get minus 3b1 equals 0, and then 0b2 equals 0. And again, we come to the conclusion that b1 equals 0, but down here we don't come to the conclusion that b2 necessarily equals 0. Instead, b2 is free. b2 can be anything. So we're looking here at the space of associated vectors is all the multiples of 0, 1. Okay, so the algebra was remarkably easy for this, and that is, of course, all attributable to the fact that this is a diagonal matrix. Diagonal matrices are so easy. But the algebra is all pretty easy, but the steps are all the same. Okay. Okay, great. There we go. Okay, so one of the things about eigenvalues and eigenvectors that I remember finding difficult about the topic when I first studied it is that it doesn't seem connected to things. When I studied, let's say, a derivative, well, I'm familiar with rate of change because I've driven in a car. When I studied integral, well, I'm familiar with accumulating continuous quantities because I've poured water into a bucket, kind of stuff. But eigenvalues, I couldn't sort of put my finger on exactly what they had to say. Now, it seems to me that that the ultimate understanding of what's happening there, it comes in studying systems and understanding what the effect of these ideas are on systems. That's to say that you can look forward to it in differential equations course. But that doesn't prevent a person from still getting a couple of ideas, look at it this way, look at it that way. And we've already looked at it in a couple of ways. In particular, we've looked at it that the eigenvalues are those x's, those values for which the vector gets rescaled by that factor. And I want to take something of a twist on that today and look at eigenvectors and eigenvalues in a related way, but draw some pictures, so some geometry. Sometimes looking at something a different way is a help, doesn't necessarily solve the problem, but is a help in trying to build an internal model of exactly what's happening here. Look at the same thing 3 or 4 different ways. Okay, enough talk. Time for some action. So let's see here. So in order to do that, I need to talk a little bit about the geometry that I'm going to do. I did some of this geometry earlier in the semester, but it was in an optional section, so a person might have missed it. But I'll go back and sort of quickly go over it again. So a defining property of a linear map is that T of RV equals R times T of V. Of course, that's one of the two conditions in the definition of a linear map. And if I'm looking at a linear transformation from Rn to Rn, then obviously it has to have that property. So T of a multiple of V is the multiple of T of V by the same factor. In real n space, Rn, a line through the origin is the set of multiples of some vector. So when I'm looking at RV, I'm thinking to myself, well, if I look at RV and let R vary over all possible real numbers or complex numbers here, then I'm looking at a line through the origin. So the action of a transformation, T, is to take R times V to R times T of V, is that the image of the domain line R times V is the codomain line of all multiples of T of V. I used a different letter because I want a person to focus their attention on you have a line here in the domain and a line here in the range. If you don't imagine that they're the same, if you imagine one's over here and one's over here, I call them R just because that seems more real to people. We could have said Cn. But so you have a domain and a codomain, and I understand that they're both Rn. But so you have a line over here and a line over here. Oops, no, a line over here. So the image of the domain line is a codomain line. Lines map to lines. Lines to the origin transform to lines through the origin. Multiples of V transforms to multiples of TV. And furthermore, the action of T is entirely determined by its effect on any non-zero vector element of the line. So if you want to see what T does to elements in this line, pick some non-zero V, calculate T of V, why that tells you what happens to every vector in that line. If, for example, this vector here gets turned from, there we go. If this vector gets turned from so to so, then every vector in the line will get turned, to whatever the geometry is there. Okay. If this vector gets flipped around to be the negative of itself, then every vector will get flipped around to be the negative of itself, whatever the geometry is Here's an example, simple example. Always a good example to reach for y equals 2x. We've talked many times that y equals x might be too easy an example, but y equals 2x is at least a start. So there's y equals 2x. It's all multiples of 1, 2. All multiples of the vector where the second component is twice the first. So I took a transformation of the plane, and I'm not I'm not a very creative person. I have 1, 2, 3, 4. I picked one that is easy, but not too easy. And it's easy to see there that 1, 2 maps to 7, 10. What that tells you, exactly what this defining property of linear transformations tells you, is that if 1, 2 goes to 7, 10, then 2, 4 has to go to 14, 20. And minus 3, minus 6 has to go to minus 21, minus 30. And in general, R, 2R has to go to 7R, 10R. So again, restated here with a concrete numerical example. That's how a person makes abstract concrete. That's how a person wraps their mind around abstract, is by having a bunch of concrete examples in their head. The action of t on any non-zero vector determines its action on any other vector in the line. I wrote the line as the span of v. I'm imagining that v is a non-zero vector. So the action of t on any non-zero vector determines its action on any other non-zero vector. If you know what happens to 1, 2, you necessarily know what happens to 2, 4, and what happens to minus 3, 6, and etc. Okay. So what does this have to do with eigenvalues and eigenvectors? Okay, here we go. If we want to understand, for example, the plane, every plane element is in some line through the origin. So to understand the action of the plane, and again, I wrote R2 and R2 just because that seems familiar. People close their eyes and instantly think of R2. Understand the action of a transformation on R2 is we only need to understand what it does to lines through the origin, because every point is on some line through the origin. So if I understood what it did to every line through the origin, I'd be done. Okay. On the prior slide, we've shown that to understand what t does to a line through the origin, we only need to understand what it does to one point in that line. So again, I'm reducing the idea of understanding the action of t to the action of understanding what it does to lines through the origin. And I further reduce that to understanding what it does to one point, non-zero, point in that line. Okay. That is to say, summarizing all the previous stuff. One way to understand the action of a transformation, one geometrical kind of draw some pictures way, is to fix a set containing one non-zero vector from each line through the origin and describe what the map does on that set. And then I'll understand, in some sense, what the map does to every point in the plane. So the natural set that has one non-zero element from each line to the origin is the upper half circle. I start there. Can you see that that's a closed-in dot there at 1, 0? And then I take the upper half circle. I go in the counterclockwise direction, as is traditional. And then over here, can you see that that's an open circle? So I'm not counting that twice. The x-axis is not counted twice. There's only one point on the x-axis, namely 1, 0. The colors I'll get to in just a second, but of course this is the familiar description of the upper half circle. Okay, so just a couple of examples. That's all, and then we'll close it out. So here's an example of a plane transformation. xy goes to 2x, 2x plus 2y. And if you saw the optional presentation that we did earlier in the semester, we talked about this. So xy goes to 2x, 2x plus 2y. So this is what we call there a skew. And pointing out here what the point of the colors is, can you see that it goes red, orange, yellow, green, blue, indigo, violet kind of stuff. And here it goes red, orange, yellow, blue, indigo, violet kind of stuff. So the red points map to the red points, the blue points map to the blue point, the green point map to this. So a person gets some idea of who maps where because I included the colors. And this was a very easy program to write. I just had the program perform this action on a bunch of points, called some of them red, some of them yellow, like that, and drew it. So something a person could try for themselves. As we move through the upper half on the left, as I move through the upper half circle on the left, the transformation has a varying effect on some vectors. different vectors get their length multiplied by different factors, and they're turned through various angles. So just as an example here, can you see that the point 1 comma 0 is turned through an angle that looks, I don't know, it looks to me like a pi over 4, but maybe that's not right. But anyway, the 1, 0 is turned here. In addition to being made longer, being multiplied by a factor of, I don't know, is it 2? I don't know. It's also turned through some angle. Other vectors may be turned through a different angle or rescaled. These ones don't look nearly as far from the origin. Are these indigo? The indigo ones don't seem to me to be nearly as far from the origin as the yellow ones. So the yellow ones are multiplied and turned, but they're multiplied by a much bigger number than the indigo ones are multiplied by. So we get some picture of the varying action of this transformation on different lines in the plane. Okay. So just as an example, I looked at what happens to 1, 0 and what happens to cosine pi over 6 sine over pi over 6. In other words, the point that is at pi over 6 on the upper half unit circle. And I drew. Okay, so the starting 1, 0 is there in red, and the effect of the transformation is there also in red. And you can see that it's made 2 square roots of 2 times as long and rotated counterclockwise by 0.78 radians. If you do the calculation. How about orange? So if you take a cosine pi over 6 sine pi over 6, that gets mapped to here, and you can do the calculation. It turns out to be multiplied by a factor of square root of 7, different than 2 square roots of 2. Right? 2 square roots of 2 is square root of 8. Square root of 7, and rotated by about 0.48 radians, so different than 0.78 radians. So the different vectors are having different effects, sometimes being turned quickly, sometimes being turned only a little bit, sort of stuff. Sometimes being stretched out quite a lot, sometimes not. So if I take a rubber band, I found this circular rubber band in my drawer. I'll make it into an upper half circle just to try to replicate what I'm looking at. Some of the points are rotated, some of the points are stretched away because points nearby are being rotated at different angles, being maybe made longer, made shorter, kind of stuff. So in the prior slide, what we see is that the map has different effects on different points. Okay, so I drew. I got a computer, I'm determined to use it. I drew what happens here. The horizontal axis is the angle of vectors from the upper half unit circle. So you see red, orange, yellow, green, blue, indigo, violet. You see the different points here. That's this axis here, the horizontal axis. The vertical axis is the angle through which the transformation rotates that vector. So the red vectors got rotated by an angle of pi over 4. Oh, I didn't point to it. Pi over 4. And some of the other vectors got rotated by a bigger angle. Some of the other vectors got rotated by a smaller angle. One of the vectors got rotated by an angle of 0. Some green vector got rotated by an angle of 0. That is to say, did not get rotated at all. So the action of the transformation on that particular green vector is that t of v is lambda times v. That vector did not get rotated, it only got multiplied. T of v is lambda of v. So we are trying to find a first take on what eigenvalues and eigenvectors are doing here in this particular picture, is that we're trying to find the natural point here, the point where you get a rotation of 0 radians. Okay, so here's a perhaps silly alternative definition, is that a non-zero vector that's rotated through an angle of 0 radians, or else entirely flipped to the opposite side, pi radians, is an eigenvector. The factor by which it's dilated is called its eigenvalue. And I'm going to take the angle of rotation to be in the range of possibly including 0 up to 2 pi, not including 2 pi. I don't want to have repeat angles. Okay, really only another example or two just to illustrate what can happen. Here's the plane transformation that we did in the check-in. You remember x goes to minus x, y goes to 2y. The transformation was pretty straightforward, and it came up with a diagonal matrix, so it was easy to understand. And in particular, it has a pretty simple action on the upper half circle. There's you can see, for example, that the green vector here that at x equals 0, y equals 1 gets doubled. Sure, it does. Of course it does. Look at what happens in x equals 0, y equals 1. So the green vector is now twice as tall as it was before. And intermediate vectors, meaning intermediate between 1, 0 and 0, 1 are made intermediate lengths. Some of them, the ones at the beginning, are just about 1 times as long, but the ones at the end are just about 2 times as long. Okay, fair enough. But don't miss out here. Do you see that if you look closely, that's red, but the red here is not at the start, it's at the end. So this vector, the vector 1, 0, gets flipped around to be the negative of itself. Minus 1, 0. And again, of course, when you look at it, of course that's true, of course that's true. So another point of the colors. When I draw exactly the same plot, xy goes to minus x2y. And when I draw exactly the same plot, on the horizontal axis here is is my name for the vector that is on the upper half unit circle. Namely, I'm naming them by the angle they make with the x-axis, counterclockwise angle they make with the x-axis. And what you see right at the start here is that the point 1, 0 is flipped entirely around, so it gets rotated through an angle of pi. And what you see here is that there is a point right there where this curve, it's not a line, it's kind of a curvy curve. There's a point where this curve crosses the axis. So obviously 2 interesting points in this picture are the point at pi and the point at 0, and I'll remark that this goes sort of up to, it has a sort of an open circle at minus pi. So one upper half circle vector is rotated through an angle of 0 radians, and of course that's the thing we're interested in, and of course that's what happens to vectors on the y-axis. They get not rotated at all, they get doubled. Okay, so what happens is that t of E2 is 2 times E2. That's the definition of eigenvector, is that it only multiplied, nothing else. Okay, well that's exactly the picture that we're drawing. Only multiplied, not turned. And we're also interested in those vectors that are multiplied by, those vectors that are sort of turned a full pi. So those vectors that are multiplied to be back on their own line. So this vector is not turned in the sense that it is mapped back to its own line, back to the x-axis. I don't know, I always write 1, 2, 3, 4 and type it into the computer and see what happens, and so I did. So what kind of crazy things can happen with 1, 2, 3, 4? Well, what you see is that this half circle has become a half ellipse. What you also see, did you notice that again the direction has turned? There is red, there is red. So here, to go from red, orange, yellow, green, blue, indigo, violet, you go counterclockwise. Here you go red, orange, yellow, you go clockwise. So that's kind of interesting. One thing that, again, you notice is some of the colors are stretched out, and some of the colors are compressed. So you can have that the angle through which vectors are being mapped is changing. Okay, and I drew the picture, have computer will draw. And obviously what's of interest here is that plotting the angle of each vector in the upper half unit circle against the angle through which it's rotated, I got the computer to draw it, gives that one vector has a rotation of 0 degrees, 0 radians, there we go, and one vector has a rotation of pi and minus pi are basically the same thing here, but anyway, pi radians, namely this vector right up here. And we know how to calculate the eigenvectors for this transformation. I'll leave that to you. But the point is that we find the 2 interesting spots on this graph, where the rotation is 0 and where the rotation is pi. So in both cases, the vector is mapped back onto its own line, mapped back onto the line that it defines. So one geometric picture of what's happening with eigenvalues and eigenvectors. What the heck are we talking about? Is that we're interested in those vectors that the action of the map is to map them back onto the line they define. I know that doesn't explain why is it so interesting, but it's at least one way to look at what's happening here. Okay, very good. So very exciting. That brings us to the end. We're finished now looking at the entire semester's worth of work. This is where our course would traditionally end. So I hope you enjoyed it. Hope you found it useful. Very good.